about series and parallel combination in resistors. Do we have any such combinations when it comes to springs? Yes, we do have. We do have similar kind of a series and parallel combinations, but the results, they are something opposite to what we see in the series and parallel combination of resistors. You remember, that is, when they are in series, resistors, they are series. If you remember, that is fine. You have come across, that is fine. But otherwise, we are going to do it right now only. Over here, when they are in series, we say our net resistance is equal to R1 plus R2, right? And when they are in parallel, these resistors, they are parallel. This is R1 and R2. They are in parallel. Suppose over here there is a battery and they are in parallel. This is a parallel combination. Over there we say 1 by R is equal to 1 by R1 plus 1 by R2. In case of springs, it works otherwise. Like over here, if this is spring K1 and this is spring K2, so they are in almost in series. That is, one end is attached to the other end. So over here 1 by K comes out to be 1 by K1 plus 1 by K2. Whereas when they are attached like this, this is K1 and this is K2. So equivalent spring constant, if K is equivalent spring constant, so K now in this case comes out to be K1 plus K2. So this is like parallel, this is like parallel, but the result is of this one. So this parallel is series of this and this series is parallel of this. So I have shared this comparison so that it stays in mind and you remember, in case you get stuck, let's say whether in series or parallel, what are the results like. So always remember these results, they are opposite to that of what you have done in resistors. In case you have done it, that is wonderful. In case you have not done it, it doesn't matter. We are going to do it right now. Now let's say these are two springs. They are attached to this body, joined to this wall and this block horizontally placed, and now we are going to stretch it. So this gets stretched over here by distance x. We find, and our intention is to find equivalent spring constant, that is equivalent spring constant. What is that? So we are interested in finding equivalent spring constant. What does that mean? We know F is equal to Kx, right? We know F is equal to Kx or F is equal to minus Kx. That is restoring forces there. F is equal to minus Kx, it only says that is displacement and restoring force, they are oppositely directed. Now we wish to find the equivalent spring constant of these two springs. What does it mean? It means for the same deformation, the same kind of force should be generated in that single spring which is being generated by these two springs. So equivalent spring constant is that spring constant of a spring which produces the same force for the same extension or compression as being produced by the combination of the springs. It could be 2, it could be 3, it could be anything. So over here if we see, if there is extension, so this applies a force K1 into X. X is same obviously for both of them, and this has also been stretched, so this applies force K2X. So F becomes K1X plus K2X, that is a total restoring force. Now we say let's replace it by a single spring and its spring constant is K equivalent, right? Now we define for the same extension, when the extension is same, there should be same force should be generated. This force that should be generated should be same as being produced by these two. So once again F is equal to Kx, where so F is equal to Kx, where K stands for K equivalent of the spring. Now what is F? This F should be same as being generated by this combination. So this should be equal to K1X plus K2X should be equal to K equivalent X. X get cancelled. So K equivalent comes out to be K1 plus K2. So over here when they are in parallel, these springs they are attached like this. So then K equivalent is going to be K1 plus K2. Now let's talk about when they are connected end to end. Now let's say over here this has been pulled like this. K1 and K2 they are attached end to end and in a horizontal position. Now we wish to find what is the equivalent spring constant of these two. Equivalent spring constant means for the same force we get the same deformation as in the case when we have 2 springs, 3 springs, 4 springs, whatsoever it is, and when we replace it by a single spring, then for the same force there should be same x, be it elongation, be it compression. Now if we look over here, when we apply a force F from here, and this K1 and K2, they are not identical. One may be a very weak spring, the other may be very thick spring. So when we apply a force over here, then there may be a huge extension, and there will be hardly any extension in the spring. So do not assume that is if x is extension over here or x is compression over here, this x is going to be x by 2 in this and x by 2 in this. No, it is not going to be there. It depends on what is the spring constant of these two springs, right? So when the extension is not same in both the springs, so let's take it as x1 in this and x2 in this. This has moved from here to here, and the total extension is x, and this extension is because of the extension in this and extension of this. So x1 plus x2 should be equal to x. Now it has gone from here to here, and x has been the extension. Now it is stretching over here, right? We have pulled it, F. Now once again we have reached equilibrium. There is a stretch in this, there is stretch x1 in this, there is stretch x2 into this. If we draw the force diagram, if the force is being applied this way, the same force has to be applied this way, because now this is stationary, this is not moving this way. So if there is a force being applied this way, the same force is being applied this way, the same force is being applied this way, the same force is being applied this way, and the same force is experienced by the wall, which is trying to pull it out. And we have just done, that is when you say F is equal to Kx, that both the sides there should be force. So over here we can get F is equal to K2 into X2, and for this F is equal to K1 into X1. So we had just done, that is if we apply 200 Newton over here and we apply 200 Newton over here, spring constant is 100 Newton. So we'll say F is going to be 200 Newton only. It is neither going to be 0, it is neither going to be 400 Newton. It is going to be 200 is equal to K. We had taken it as 100 Newton per meter into X. We had just done, so X is equal to 2 meter, right? Similarly over here, when you apply force over here, this has been pulled over here. Now this everything is stable kind of a thing. Nothing is moving. Acceleration is equal to 0. When acceleration is equal to 0, we are applying force this way. This force is this way onto this block, and this block through this string is applying a force F on this spring. Ultimately, this is also not accelerating. So this way also should be force is equal to F, and this they are identical. So F is equal to K2 into X2. F is same throughout the length. For this, F is equal to K1 into X1. And now x1 plus x2 is equal to x, right? So over here also we say, that is if we apply a force F, for this also, that is F is equivalent to, that is K equivalent into x. That is for the same force, there should be same extension as in this original combination. Now the whole thing is replaced by just one single spring. In one single spring, for the same force, same extension is there, same extension or same compression, anything, it could be anything. So for this, F is equal to K equivalent to x. So what is x1? If F is equal to K1 x1, so x1 is F upon K1. We can write it like this, F is equal to K1 x1, so x1 is equal to F by K1. What is x2? Plus x2 is F by K2. Now what is x? X is now F over K equivalent. F, it can be taken out and can be cancelled. So it comes out to be 1 by K1 plus 1 by K2 is equal to 1 by K equivalent. We get the result. So equivalent spring constant is spring constant of a single spring which for the same force produces the same deformation as being produced in the combination of springs. So these combinations, they are primarily series or parallel. These are basic combinations. And using this combination, you can have a multiple kind of a combination. So they are two basic combinations of the springs we can have. And if we have many number of springs, we can have few in series, few in parallel, and to them also something in series, something in parallel, and we can have various combinations.